Our world of sound spans incredible extremes, from a faintest whisper to the roar of jet engine. These sounds differ in pressure by millions of times. In this video, I'll explore the concept of decibel or dB, a unit that helps us to compress this enormous range of sound pressures into a simple and human-friendly scale. Let's start by talking about what sound really is and how our ears detect the sound. Sound is a pressure wave, a mechanical force that pushes and pulls air particles. Imagine a guitar string vibrating. Those vibrations squeeze and stretch nearby air molecules, creating alternating region of high pressure and low pressure. By definition, pressure is force divided by area, and its unit is Pascal. 1 Pascal equals 1 Newton of force acting on 1 square meter of surface. In air, the smallest sound that the average human ear can detect is about 20 micropascal, or 20 times 10 to the power of minus 6 Pascal. It's incredibly small. This tiny pressure changes act on the air drum, which has a certain area, and that mechanical movement is what sends a signal to our brain. Now, let's think about how our brain interprets differences. Suppose you hold two objects. One weighs 90 grams and other 120 grams. You probably say object A is 30 grams heavier than object B. That's a linear way of comparing. We look at the difference. But if the objects were 1 kilogram and 3 kilograms, we don't say most likely A is 2 kilogram heavier. Instead, we say A is 3 times heavier. So, as the magnitudes grow, our perception shifts. We start thinking in ratios, not differences. This ratio-based or logarithmic way of perceiving is how our senses naturally work. Whether it's sound, brightness, or even weight, the same idea applies to sound pressure. If we list pressures for different sounds, from a rustling leaf to a jet engine, the numbers vary over millions of times. That's far too wide to compare directly. So scientists defined a new unit based on ratios to make this range manageable. That unit is the decibel or dB. We start by choosing a reference pressure. 20 micropascal, which represent the threshold of human hearing. If a sound has 20 micropascal, the same pressure level as a reference pressure level, we call it 0 dB. We do not know yet dB, just name it 0 dB. If sound pressure is 10 times stronger, gives 20 dB. 100 times stronger gives 40 dB, and so on. The loudest sound our ears can handle before pain, about 1,000,000 times the reference pressure, corresponds to roughly 120 dB. So, the entire range of human hearing from threshold of onset of hearing to pain fits nicely between 0 and 120 dB. Mathematically, we express this relationship using a logarithmic base 10. As L equal 10 multiply log 10 Q divided by Q reference, where Q is measured quantity and Q reference is the reference. If our quantity is something like pressure or voltage, we use the factor 20 here. The formula is the same. We rewrite this formula as 20 log 10 P divided by P reference. If our quantity is power, energy, intensity, we rewrite this equation like this. L equal 10 log 10 capital P divided by capital P ref, which P is power here, P ref is reference power. Let's work through a few quick examples to see how this helps us. Suppose our reference pressure in air is 20 micropascal. If we measure a sound that is twice that pressure, say 40 micropascal, plugging it into the equation here, we get plus 6 dB. So doubling the sound pressure equals plus 6 dB. If the pressure is 10 times higher, it becomes plus 20 dB. If the pressure is 100 times higher, it becomes plus 40 dB. You can see how easily this scale compresses massive changes, turning millions of pascals into simple numbers between 0 and 120 for a range of course, human hearing only, as an example. That's the beauty of decibel. It takes a complex, wide physical range and expresses it in a way that matches how we actually hear. So, to summarize, sound is a pressure wave acting as a force per area on our eardrum. Our ears respond logarithmically, not linearly. The decibel is a ratio-based logarithmic unit that reflects how our brain perceives sound. Thanks.